The best way to break this addiction is through technology.
Have you ever seen this before, Bob?
Never, never.
And we are on the threshold of incredible
Good thing you
advances.
didn't copyright it.
Cutting-edge methods of producing ethanol, not just from corn, but from wood chips and stalks or switchgrass. Our goal is to make this new kind of ethanol practical and competitive within 6 years.
That was from Richard. I like using that clip. It gets people's attention. I'm really happy to be able to introduce a very good friend of mine and someone who has a very unique, and very in-depth knowledge of biofuels and energy and using plants for biofuels. And I'm pleased to be able to introduce Richard to those of you here at UCLA and those of you who are sitting up in Davis. Richard has a really unusual and remarkable background. I've known Richard now almost 12 years, and we're very good friends, and he's done some remarkable things. But his background is unusual because, as I told you on Tuesday, he has an undergraduate degree in biology. He's got a PhD in molecular biology from Vanderbilt University. He was a Howard Hughes Medical Institute postdoctoral research fellow doing cancer research at Harvard. And then he decided that what he really wanted to do was be involved in the biotech industry and translate many of the basic discoveries into practical applications that not only can help humanity, but also can capture some value and make some profits. And so Richard and I met each other when Cirrus was founded, and I told you a little bit about that on Tuesday, back in 1992, Jesus, a long time, 1996, 1997. That's because after Richard was working on his postdoctoral research in Boston and Harvard, he decided to go work for a venture capital firm. And that is that what his job was to fund startup biotechnology companies, look them over and help them get started. And the company that he was working with was one of the founding investors in Cirrus, and Richard's job was to oversee the company for that investor. But on the other hand, he became so excited about plants and so excited about the prospects of making a new company very successful and taking it from research and development to products, he decided to come and work for Cirrus as its chief financial officer. And then after a few years, he became the chief executive officer. And the company has moved from research and development, a basic genomics company, discovering and trying to determine the identity of genes that are important for agriculture. But Richard, from the beginning, always said energy, 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 energy. And I think that the moons are aligned quite properly now. And as you'll see, he's going to talk not so much about what the company is doing, but he's going to give you a global view of making energy from biomass, both the problems and the prospects and how exciting that is. And so I'm going to turn the floor over to Dr. Richard Hamilton, and let's give him a big round of applause. He's very busy, and I almost had to...
Bob.
We need a microphone for Richard. You have it?
Great. Wired up.
Yeah, I had to twist his arm to come here today, but I also will tell you that he had about 10 meetings between 6:30 in the morning and now. So
you had to twist my arm?
Yeah, exactly.
Somehow the idea of physically intimidating me, Bob, is not really going to fly. Okay, so I don't typically sing for my supper. So try not to give me a blank stare. Like if you understand what I'm saying, go like this. If you don't understand, go like this, okay? Be interactive, ask questions. If I go too fast, okay, got it. So I'm going to try and give you some perspectives on fuels. And Jim Woolsey, who used to run the CIA, described this perfect storm that we had last year of demand trends. And you guys know all this. As China and India industrialized, demand for fuels goes up. We have, until very recently, with the collapse of the global economy, had high oil prices. You've heard this word energy security a lot. And it's not just for the US. China also imports about 60% of her petroleum, right? And so put yourself in her shoes, right? Does the Chinese Navy control the Straits of Hormuz? It does not. The United States Navy does. So how do you think China feels about that and energy security? So energy security is not only a US issue. And you're hopefully all aware of the environmental concerns that come from combusting carbon-based fossil fuel sources. Yeah? Everybody go like this. Good, okay? So where can we find this significant renewable domestic source of transportation fuels? Next slide. So let's take a little quiz. This is supposed to be A, B, C, D, E. Yeah. So just to establish a baseline, you're going to have to take notes on this, Bob, because we're going to have to compare the baseline.
Well, we have a report on the computer.
But then we're going to actually see if a UCLA professor can use an Excel spreadsheet and generate a graph.
That
okay.
I can't.
Okay. So in the future, we're going to get transportation fuels from electric cars, hydrogen, conventional oil and gas, thank you, Exxon, biofuels, or hot air from UCLA professors.
So you got to start it.
Well, how do I do that? Oh, I got to do this now? Can you sit here and do this every time? Okay.
Then you go start, you let them go for about 15 seconds.
Yeah.
And then you go stop, and then display.
Okay, did everybody vote? You can hum the Jeopardy theme, Bob. Do, do, do. Come on. I don't want it. All right, here we go. Let's see. And then I hit display. And, oh, come on, biofuels already? Somebody see, this is what happens when you give them the slides in advance, Bob. All right. Now how do I hide this? Oh, maybe the big thing that says hide? Even a PhD can do it. Okay, so let's talk about electrons. And a lot of money getting spent, in the Obama stimulus plan on battery technology and electric propulsion technologies. And so Thomas Friedman coined this term, clean electrons. So aren't clean electrons the answer? We can use CSP, which is concentrated solar power, right? These are all mirrors that are going to concentrate the sun's rays. You're probably all familiar with photovoltaic, wind, geothermal. I'm not sure how clean people would consider nuclear power to be, and I'm not sure there is something called clean coal. But we're going to take all these clean electrons and we're going to drive electric cars. And some of them are kind of sporty, right? You can just see that could be Bob Goldberg driving down PCH in his Tesla Roadster. And we have the Chevy Volt, of course, which everybody right knows is an all-electric car, right? Yeah, okay, we'll come to that. So yeah, why not clean electrons, Rich? That's clearly the way to go. Do I have to be like right on top of this thing? Okay, a little bit of a problem. Today, solar is about 1/10 of 1% of the US power grid. Wind is about 2/3 of 1% of the US power grid. So right now, making more electrons is going to mean burning more coal, right? Because coal is 50% of the grid. Question right there. Ask the question again.
Okay, so solar energy constitutes how much?
Yeah, so solar energy right now, in terms of installed capacity, okay, is about 1/10 of 1% of the US power grid. So we got a long ways to go. By contrast, coal is about 45% or so. Okay. Okay, so we'll just build more wind and more solar, right? Which we're going to do anyways. Okay, well, let's stop and think for a second. Where does a barrel of oil go? And as it turns out, we use oil for a lot of things, right? We use oil not only to make gasoline drive cars, but we use it to make plastics and other petrochemicals. We use a lot of diesel for a lot of things, right? And I don't think we're going to fly in electric jets anytime soon, okay? So when you do the math, about 44% of a barrel goes into gasoline. And of that 44%, about 48%, or about 21% of the barrel is passenger cars, okay? And so then ask yourself, of that 21%, how much are we going to be able to use in sporty little electric cars? Because the problem with electric cars is that they need to be little. They need to be little. And they need to be little because the battery starts chasing you downhill. Okay, so it works for Bob's little Tesla Roadster, but when my wife gets in her all-electric minivan and gets stuck on the 405 with her windshield wipers on and her headlights and the heater on and the radio playing, today's battery technology will take her about 5 miles, right? Not very far at all. So it's really tough to get there. And some other smart people, well, we'll get there. So Chevy Volt, all-electric car, right? Wrong, okay? It's got a range of about 40 miles when you run it on just the electric motors. It has a 4-cylinder, 1-liter gasoline engine. Doesn't drive the drivetrain, drives an alternator to recharge the battery. When you do that, the range goes to be somewhere between 150 to 300 miles, depending on whether you drive like me or you drive like Bob, okay? So does it still need liquid fuel? Absolutely. Okay, here's my wife's minivan. It's just that the battery technology isn't there anytime in the foreseeable future. So these technologies, as I'll say over and over again, hybrid technology, plug-in hybrid electric technology, they can improve fuel efficiency, and we should absolutely deploy them. But they cannot do away with the need for fuel. This is a slide. This is a slide from the Toyota Motor Company. I was asked to present at the Aspen Institute this summer, and Toyota Motors presented this data. And what they said was, they said, look, this is a highly unrealistic and highly improbable scenario, but if 100% of US new light truck and new car sales were 100% hybrids starting in 2010, 100% of the fleet, and right now hybrids make up well less than 5%, right? So you got to go to 100%, and in 2020, 50% of all new cars are plug-in hybrid electric vehicles. Then basically, as I read this graph, by 2030, your oil consumption is back to where it was in, maybe 1999 or so. So again, you can improve fuel efficiency, but you can't do away with the need for fuel, okay? Unless everybody's going to have less than 5-mile commutes. Yes?
Is that based on the nation? Because there are a lot of parts of different states I would imagine have different percentages for how many use hybrids.
Exactly. So depends on the geography, right? So Southern California, solar rich. If you live here in Westwood and commute here in Westwood, right? A plug-in hybrid or even an all-electric car is going to make perfect sense. Can anyone tell me what the #1 selling car was in the United States in the month of December? Prius? Anybody? #1 selling car in the United States in December was, no, Ford F-150 pickup. Ford F-150 pickup. Middle America doesn't commute 5 miles. Nothing even close to it. Okay, so let's keep going. Meanwhile, oh, sorry, question.
I just have a question about hybrid buses.
Yep.
How much does that eliminate fuel? Or is that taken into account as well, or is it something separate?
That only looked at, they did not account it for changes in public transportation in their analysis. They just looked at the things that they changed were the passenger vehicles.
Okay.
So again, you shouldn't come away like hybrids are a bad idea. That's not the idea. Or that plug-in hybrids are a bad idea. We should absolutely do it, okay? But you're not going to replace fuel. The idea that you're going to run your transportation grid on solar and wind power, I think is a big mistake. Okay, so meanwhile, you guys probably recognize Beijing. Up until this economic crash, the Chinese were adding 1,000 new cars per day in Beijing alone, registering 1,000 new cars a day in Beijing, right? And the car penetration in the Chinese market, I can't remember. I think we have about 1 car for every, certainly more than 1 car per household. In China, it's like 1 per 100, thereabouts. So they got a long ways to go and a lot of cars to be built and driven on which one presumes they're going to want to have performance like we have. Anyway, this car is from an Indian company called Tata. It's called their Nano. And it is a 4-cylinder internal combustion engine car. And its retail price in India today is $2,500. Okay, the price for 25 kilowatts of battery for a Prius is $17,500. So not only are you not going to get the performance, India can't afford it, right? So you're still going to have low-cost internal combustion engine technologies, okay? So let's vote again. Bob, Jeopardy theme song, please. Let's see. What were we at the first time? What was the vote the first time? Did you record the numbers? 46%. Let's see if we did any better. How many voted for hot air for UCL professors? So, yeah, baby. Okay, so conventional oil and gas. Okay. I don't have the really scary slides about peak oil and all that, but oh, there's the hide thing again right there. Okay, let's keep going. How much time do we have? We'll go all night here or what? Okay. Okay, so hydrogen. Let's just some thoughts on hydrogen. I sort of put these together. So hydrogen, people will say, is the most abundant element in the universe. Unfortunately, most of the hydrogen is usually bound to something else, unless you happen to be on the surface of the sun. Okay, so it's kind of hard to get free hydrogen. Does anyone know how hydrogen gets made today? Any chemists in class at all? No. Bob? Hydrogen today? Hydrogen today gets made by steam stripping natural gas. So they take methane and they heat it up like crazy and they strip it off and they get CO2 and they get hydrogen. So it's not it's how are you going to make it, right? You're making it today from fossil fuels. You could conceivably make it from the electrolysis of water, right? So you generate solar or wind, you generate electricity, and then you hydrolyze water. You split water, you get oxygen and hydrogen. Really, really, really expensive, okay? And I don't think I have it on the slides, but it's something like $60 a gallon is where it comes out today. So you're going to have big, big, big improvements. So maybe we make it tomorrow through electrolysis. Once you do it, you still don't have a storage and transport infrastructure to do it, right? So you've got this great infrastructure by which we can move liquid fuels. Today we're moving petroleum and gasoline, right? But think about it, right? You can get on Interstate 10, so 10 goes across the country, doesn't it? You can get on Interstate 10, drive across the country, and pretty much, I don't want to say every exit, but every third exit or whenever you need it, you can pull off and there's a gas station, right? And so there's an infrastructure to move this stuff around. Hydrogen, really, really hard to store and move, okay? So what we really want to do, unless we want to invest trillions of dollars in a completely new fuel transport infrastructure, is use the one that's in place, but replace the petroleum that's in there today with something else. So, some quick facts on biofuels. So, whereas solar is 0.1% of the U.S. power grid, okay, and wind is 2/3 of 1%, biofuels are already about 10% of the U.S. fuel supply. Now, that's a little bit unfair, right, because I just compared fuel with power, right, but nonetheless, transportation fuel with power, but nonetheless, that's where it is. They also use about 15% of the U.S. corn supply, because in the United States today, using the available refining technologies, we make biofuels, we make ethanol from cornstarch, okay? Lest you think that we're starving people by doing that, remember that most of the corn in the grocery store is in the meat aisle. So 80% of the corn grown in the United States goes into animal feed, 15%, right? So 95% of it is either going to ethanol or animal feed. Very little goes directly to feed people, very, very little, okay? You might also be interested to know that ethanol actually has a higher octane rating than gasoline, So if you run it in a high, for any car folks right there, if you run it in a high performance, high compression engine, you actually can get better performance, better torque than you can out of octane. Yeah.
Isn't it cheaper to make it from sugar cane?
Yes. We'll come to that. Why is it cheaper to make it from sugar cane?
Because has more sugar in it, more sugars.
Yeah, so from when you compare the amount of starch that you get from a corn plant to the amount of sucrose that you can get, that you can press out of a sugarcane plant, where is there more sugar was one question, right? And the answer to that is, yeah, a little. There's a little bit more there. What's minimum wage in the United States today? Anybody tell them? It's around $8. Around $8. Anybody know what a Brazilian sugarcane worker makes per month? About $200 per month. So the dirty little secret of Brazilian sugarcane is that their farm labor costs are ridiculously low relative to ours, and so that's one of the reasons it's so much cheaper on a per gallon basis. If you look at sugarcane yields in Texas, the Brazilian they lag the Brazilian yields by about 5 or 10%, but their cost per pound of sugar is more than double, and it's all in the labor costs. So what we have in the United States is we have something called the Energy Independence and Security Act, was passed in 2007, and a lot of people don't like cornstarch, but Midwest corn farmers like it a lot because they want to create demand for their products. And what we've done is we've capped that at 15 billion gallons. We're at about 10 billion gallons today. We put in about 1 billion gallons of renewables, or excuse me, biodiesel. Advanced renewables are things that are made for just anything besides corn, falls into this advanced renewable. So if you make it from grain, sorghum, or wheat, or whatever, you can use that. And then cellulosic and biomass come out to be another 16 billion gallons. I think this is 5 billion. And this whole thing adds up to about 21 billion gallons. And the whole thing should be about 35, 36 billion gallons by 2022, which is 14 years away. So we have our work cut out to do this, because whereas the infrastructure is in place to do this, there are 134 cornstarch to ethanol plants in the United States. There is so far one operating cellulosic biomass to biofuel refinery in the United States. So a lot of steel needs to be put into the ground to build the refining capacity to do even this bit. Okay, so the biggest drawback of biofuels is what? They cause food prices to rise. They're going to starve the poor. We're going to cut down the Amazon. They can't scale to be something significant, or they cause childhood obesity. Let's see. Where did he go? Oh, the question is, what is the biggest drawback of biofuels? You sort of can't see the question because it's up behind the. Excuse me? Oh, can they scale to be something significant? So if you do the math and you use like 100% of the U.S. corn supply, it would come out to be like 30% of our gasoline supply. So it could never be 100%. So scale means how material of a solution could they be? Votes. We display. 1, 2, 3, 4. So they can't scale is everybody's concern. Can you make a material amount of fuel and causing food prices to rise? And we're going to talk about that. Okay, let's keep going. Okay, is there a way to move this thing, Brandon, so that it's someplace else? Because it's in the title of all the slides. There we go. Just leave it to the side there. Yeah. So the opportunity for biofuels. So Steve Koonin, who I like to call better than average smart. He's a theoretical physicist. He was the provost down the street at Caltech. He took a job 3 years ago now, I think, to become the chief scientist at BP. And he said, with plausible technology developments, biofuels could be 30% of global demand. But to do that, you need to get to something called dedicated energy crops separately and distinctly from food. And we're going to explore why he thinks dedicated energy crops and why I think dedicated energy crops are a relevant feedstock for biofuels. So, a little bit of carbohydrate biochemistry, and it won't hurt. But you mentioned sucrose and sugarcane, right? And sucrose, which is table sugar, is simply a molecule of fructose and a molecule of glucose. And it's easily hydrolyzed and fermented, and off you go to Brazilian ethanol, who, by the way, Brazil now runs their domestic transportation economy on sugarcane ethanol. They no longer import petroleum to run their economy. And the sales of what are called flex fuel vehicles, vehicles that can run on either 85% ethanol or regular gasoline, now make up something like 85% of new car sales in Brazil. So this can be done. It can scale, again, something like 18 million vehicles in Brazil, so slightly smaller than the United States. But you can, right, as I said, off you can go to biofuels or mojitos, as the case may be. And if you want to grow as much sucrose as you can per acre, then you're going to grow sugarcane. Okay, that's your choice of crop. Now, starch is a polymer of glucose. Okay, and you can think of it as like beads on a strand. And using enzymes, which I always describe as little Pac-Men, you can come along, cleave these bonds, release these free sugars, and off you go to biofuels. In our case, mostly ethanol in the United States. And in case anybody's interested, you can these glucose molecules, you can also treat with an enzyme called fructose 1,6 isomerase, I think, and voila, high fructose corn syrup, which take a walk down the soda aisle. That's where it all is, right? So that's the basis of a corn dry mill, and that's where we're making about 9 billion gallons of ethanol today. Now, far and away, most of the carbohydrate in a plant is in the form of cellulose and hemicellulose. It's what plants make their cell walls out of, okay? So you guys are all too young to remember. When did Dukakis run for president? Like 80, 88, something like that? And he interviewed this guy, Willie Horton, who was a convicted bank robber. He said, Willie, why do you rob banks? Willie said, that's where the money is. So, of course you should rob banks because that's where the money is. Well, of course you should go after cellulose and hemicellulose because that's where all the carbohydrate is, even in a sugarcane plant, right? The sucrose is I think the BRICS values that the Brazilians are up to is about 13, 14%. That means about the remaining 80% or so is in cellulose and hemicellulose. And the problem historically has been is that this stuff is very difficult to refine, okay? So looking at just biochemical processing for the moment, these Pac-Men, these amylase and glucoamylase are on the order of about 2 to 3 cents per gallon. The cellulases and hemicellulases to do this 5 years ago were about $5.50 per gallon. They're now down to about 35 cents per gallon and going further. There's also other thermochemical and catalyst-based technologies that people are working on to do this. But if you can do this, now you can start to get a lot more fuel per acre, okay? And that's what's shown here. This looks at this is data from the DOE, and it's looking at something they call the fossil energy ratio. So those of you who are not big fans of corn farming know that you actually have to put a fair amount of energy into a cornfield, right? You have to put diesel in, you have to put fertilizer in, and as a result, yep.
Is that cellulose? Could you get that from algae?
Testing.
Algae don't make a lot of cellulose, but they do make lipids, which you can turn into diesel fuel. So I don't know that I have any slides on algae as a fuel producer, but the big limitations are cost. So right now the algae guys, they go one of two ways. They go these open pond systems, which still cost a lot of money. It costs about $100,000 to make an algae pond. And then you have relatively low productivity algae simply because stuff blows in on the wind and the ponds keep getting contaminated. So the National Renewable Energy Labs tried this in the late 70s and early 80s, and they shut the program down. Some people have started things back up, but I think compared to mature cellulosic refining technology, it's going to be tough for algae to compete on a cost basis. So getting back to the point that I was trying to make here, the net fuel, when you're only using the cornstarch, these numbers range from sort of 1.2. There's actually one guy in the world who thinks it's negative. A guy named David Pimentel at Cornell thinks you have to put more energy in than what you get out. The highest I've ever seen is sort of 1.6, but everybody agrees it's not 5 or 7 or 10. But the estimates for cellulosic are sort of between 10 and 12x. So for every gallon of fuel that I put in, driving the harvester, transporting the biomass, et cetera, we can get about 10 gallons back out. So it has a very positive net energy ratio. Oh, up to 86%, okay. But we doubled the hot air from UCLA professors, watching that carefully. Okay. So a number of people, you've probably heard this in the press, say, oh, biofuels drive up food prices. Well, fortunately or unfortunately, we've done the experiment. And we have seen a collapse of global oil prices. And I think it closed today around $34. I haven't updated my slide. But look at what's happened. In parallel, corn prices have collapsed. Okay? Ethanol production volumes have continued to go up. How'd that happen? How is it that ethanol production volumes are not driving corn prices? I can't figure. See if I, so why is that? Why is that? Well, it's just pretty basic biochemistry and economics, right? Cornstarch, it could be potato starch, it could be sweet potato starch, it could be any kind of starch out there. It is fungible into ethanol, has been for 4,000 years or so, okay? Ethanol competes with gasoline. The price of gasoline gets set by the price of oil. So what happens? If the price of this goes up or down, the price of this goes up or down, the price of this goes up or down, ooh, guess what, right? The traders at Cargill aren't exactly stupid, okay? So they can sit there, and when they know what oil is going for, they know what corn should go for, because it's fungible. So whether we like it or not, our food prices are very tightly linked to the price of oil. And when the price of diesel goes to $4 and $5 a gallon, the price of all food is going up, okay? Let's vote again. Maybe we're voting too many times, I don't know. We're already at 87%. I'm going to declare success. So there's 25 voters. Is that what that 25 represents? Okay. Okay. So, oh, okay, we shifted down. So we still have a number of people who are worried about food prices. Good. You should. What's that? Oh, sorry. So one of the misperceptions that many people have about agriculture is that they believe that it's both uniform and static, and it is not. So these are US corn yields, and we have very good data for Indiana going back to about 1865 or so. And you can see that we sort of bumped around at sort of 25, 30 bushels an acre for, what do you want to call that, 40, 60, about 70 years, okay? Through the advent of commercial fertilizers, right? Nothing doing. And then we began to adopt hybrid genetics. Anybody know what hybrid genetics is, or hybrid vigor? Have you guys learned that? Are you going to teach that? Okay. Basically, it's the opposite of what happens when cousins marry. Okay? So you take genetically distant parents, you cross them, and you get a hybrid. You get a hybrid vigor. You get something that outperforms the parents.
All of you guys are hybrids. No ifs, ands, or buts. Even those of you up in Davis, you're hybrids.
Okay? And what we've done is through what is called double-crossed hybrids, then single-crossed hybrids, and now with the adoption of biotechnology, we have increased corn yields in the United States by 500%. 500%. And in fact, remember we heard about all the floods in Iowa this spring, right? Was it, right? They declared Des Moines a federal disaster area. In spite of all that, we had the second highest corn yields ever. So hybrid genetics and biotechnology, right, changes the game in terms of how much yield you can get per acre. And when they looked at that 15 billion gallon cap in the renewable fuel standard, they said, corn, we're going to cap you at 15 billion. What they assumed in that is they looked at the projections for further corn yield increases, and they said that all of that 15 billion gallons should come off existing acres as a result of higher yields. Okay? Not enough food in the world. This is one that people seem to believe. This is the cover of Scientific American a little over a year ago. But the simple fact is that the number of clinically obese people in the world outnumbers the number of malnourished people now about 2 to 1. So you might not agree with how food gets distributed in the world, and you probably shouldn't, but there's plenty of it. Okay? There's no question about that. Okay? And those 800 million people, right, I got to tell you, they don't care whether corn's at $4 or $6 because they're all living on less than $1 a day. They can't afford it in any case. So what we'll hopefully learn here is that hunger is more about poverty than anything else. It's more about poverty than food availability. Okay? About 60% of global corn acres are hybrid varieties. That means today, 40% of corn farmers in the world are outgrowing corn the way my grandfather did and getting 30 bushels an acre. Okay? Not good. About 50% of global rice varieties are hybrids, although the Chinese are going fast and furious on this and seeing significant yield increases. And so increasing yield is the answer for both food and fuel crops. Food must be too expensive with all these biofuels, right? Maybe not. And this is data from the USDA's economic research data looking at the percent that people in the United States spend on food expenditures. And while the total is still pretty high, a lot of it is because we eat out a lot. And, but nonetheless, it's come down pretty dramatic. I think this goes back to just around the Depression. So food is clearly not too expensive. Here's some sobering corn yield data. Was it the finance minister of India called biofuels a crime against humanity? Well, I think the real crime against humanity is Indian corn yields, okay? Because here's the United States, right? We're now at 155, I believe, for the 2008 growing season. And yet, why are these yields so low? It's again, open pollinated, non-hybrid corn varieties, lack of farming infrastructure, right? So there's the world average is less than half of what we get. And this is just corn. Don't think that it's a whole lot different for soybean or wheat or many other crops. Are we running out of food? Well, this is data from the UN's FAO stat database. And what I did, I looked at 3 major grains, corn, wheat, and rice. I looked at one non-food crop because we certainly use plenty of cropland for non-food applications today. And I took the top 10% producers and asked what is their average yield kilogram per hectare, called that 100%, and then asked what is the global average? And in all cases, right, it was less than 50%. And the bottom 10% was abysmal. Okay? So we really don't have a shortage of cropland. We have a shortage of agricultural technology. And so the answer is yield, mainly through germplasm, genetics, right? Agronomy, crop protection, farming. This is just an example of the kind of yield potential that exists in some geographies. This happens to be in Malawi. And Mary Katsiana's harvest in 2005, growing open pollinated varieties, right? And of course, saves her seed year to year, right? But that's what the open pollinated varieties are going to do, right? In 2006, $70 worth of hybrid seed and fertilizer, and the yields went up almost tenfold, okay? The next year, she had the option, right? You want to go back to your saved seed, or do you want to buy more hybrid seed, right? She chose the hybrid seed. This is what US corn farmers have been doing for 7 years. Drives some people nuts. Drives them nuts because they say, oh God, you're now dependent on the seed companies. Well, there's more than one seed company, and for the seed companies to make money, they need to get better and better every year, which they do. Unfortunately, poverty is mainly caused by poor governance. And if you ask yourself, well, why can't Mary and her neighbors all go out and start growing hybrid corn and send these yields through the roof? Well, what's Monsanto's pricing? It's about $350 for a bag of corn seed, I think. So when a US corn farmer goes out and he needs to buy seed for next year, right? Do you think he has that money just sitting around in the bank? What does he do if he needs to buy seed or if he needs to buy a new tractor? What does he do? Takes out a loan. What does he use for collateral? His property, his farm. Why? Because he has a title to that land. Most of the farmers in the developing world don't have clear title to their land. They're in effect squatters. So there's a whole set of mechanisms, land titles, access to credit, agricultural infrastructure, all these things lead to low agricultural productivity, not, oh my gosh, we're running out of cropland. Here's an interesting question. I'd be interested to see your answers. Is food a market good or a public good? Okay. Does everybody know what a market good and a public good is? So a market good is something that's freely traded, right? Right, buy it, sell it, gets traded on the Chicago Board of Change or NYMEX, right? Oil is, as you'll see in a second, oil is clearly a market good. Okay? Some things, drugs are a good example. Some people believe drugs should be public goods. In other words, drugs should be discovered and then sort of just given away freely, okay? So critics of biofuels seem to think that US, or certainly US corn farmers should, feed the world by producing at or below their production costs. Because I gotta tell you, at $3 corn, they're barely making it. Most corn farmers will lose money, and especially if you take the crop subsidies away. They'll lose money, okay? So some people think we should just keep corn prices as low as possible. Corn farmers not among them, by the way. But yet, come on, build. Nobody seriously expects the Saudis would fuel the world by selling oil at or below their production costs. Anybody know what Saudi Arabia's average production cost is for a barrel of oil to lift? Average lift cost? Anybody know what the deep water stuff in the Gulf of Mexico goes for?
What do you think? $1 a gallon?
Barrel,
a barrel? $2?
Barrels.
Barrel.
So the deep water stuff in Gulf of Mexico is about $40. So just to give you a comparison, Saudi Arabia's average costs about $4. So anybody think that the Saudi Arabians should just subsidize global oil production?
How many gallons from a barrel?
42.
Think about that.
That's their lift cost.
Costs them $4.
So again, it's an interesting question, and my answer for food is it's kind of both, right? But nonetheless, we're going to vote on whether it's a market good or a public good. And the questions I put down here, I'll go ahead and start this, right? A lot of people view, hang on just a second, people view healthcare as a public good. Some people view higher education as a public good. Your parents probably view it as a market good.
Is that a question of whether it should be a market good or
Well,
public good?
what do you think it is? What do you think it should be?
Should be, got it.
Well,
Whatever you
whatever.
want. What do you think it should be in the world?
Isn't that what we're voting on?
Yeah. Should food be in the world a market good or a public good? Just give it away for free. Everybody vote? We had 28? Yeah. Okay, so 40% of you think that food should just be a public good. Interesting.
Who said it was going to be a public good?
Should
Davis?
be a public good.
How many public good, market goods? Public good, Dora? Can't hear you.
Yeah.
Can you tell us why you think it's a public good?
Because I think everyone should have access to food.
Who's going to pay for the farmer to grow it?
The government. The government does everything for us.
So you're going to be willing to pay taxes in order to pay the farmer to grow the food that you're going to eat for free?
Yes.
And you think that someone's going to work 100 hours a week to farm because it ain't easy to be able to make no profit, not to be able to make a living? How many of you people are going to school because you want to get a job at some point? Can I see your hands? How many people in this room would like to get a job at some point where they'd make a significant amount of money to be able to buy a car and a house and be able to have some kids and send them to college and do all those things. Costs money, doesn't it? Zach, do you want me to hand you the money in order to do that? Oh. No, seriously. Yeah, should we just give it away?
Well, I would obviously want to just be given money, but I don't think that's a logical or reasonable option.
Can you tell us one experiment in the 20th century where they felt they could just give everything away for free and tell us how successful it was?
Probably not very successful.
What was the system? Does any of you know? Albert? Yeah, it was the Soviet Union. Collapsed. Stephen, get a microphone. Faria, do you agree or disagree?
I agree.
Agree with what?
I think that, I mean, it sounds nice to make it public so everyone can get food, but it's easier said than done.
Yeah, I don't know about the rest of you, but I like people to show me the money. Go ahead, Richard. Stephen, go ahead.
Hey, go ahead, Steve.
The point of it being a public good is that individual humans have inalienable rights that, and food should be one of them. Nourishment should be one of them.
What would be your system to be able to provide all this food at no cost to people?
I'm not saying at no cost to people, but as a public good through a more communal program.
Such as?
Such as, I'm not a legislator, but I...
Okay, so in just responding to that, and then I'll turn the floor back over to Richard, when Soviet agriculture went to communal systems instead of individual market-oriented farmers, it completely collapsed and caused a famine that killed 30 million people in 1 year.
I'm not saying that particular process was the best way to do it, but I'm saying that it's an atrocity that we have the food and we can have the food, but we still have people starving to death.
Well, we're all in agreement with that.
So I think what it comes down to is it's a good conversation, and again, I don't really have the answer. I just sort of put it up there.
Randy?
I think what you want is you want to have some safety net, right? If you have a safety net, that's that people will say, well, I'll have it be a market good as long as there is a safety net, right? That begins to make a lot more sense, and that's where I sort of cheat and say both, right? Because higher education, just as an example, one that is sometimes a little less emotional than food, right? But you say, well, higher education, clearly a market good, right? Your parents see it as a market good, I assure you. But at the same time, you say, well, to people who are deserving, we ought to make higher education available, right? If you have very smart people, you should make higher education available. So you want to have that safety net. And it's a hard question, right? It really is. And when you view it, there's nobody here from the Midwest? Nobody? Anybody know, sort of, like Chicago? We used to live in Indiana, right? So what's the average size of an average U.S. corn farm? Anybody know? 100 acres? It's about 2,000 acres, right? But everybody, right? You think that corn farmer, right, who's married and has a couple of kids, you ought to be able to grow up and send his kids to college, right? Right? That's the average, right? So okay, so let's do some math now. So 2,000 acres. Let's call it 200 bushels an acre. Bob, do the math for me. So that's 4,000, couple of zeros, right? Right? So 4 times 10 to the 5th, are we at, right? So that was at 200 bushels an acre times $2, right? That gives us 8 times 10 to the 5th, $80,000. Am I doing that math right? $800,000 gross, right? $800,000 gross minus his expenses, which at $2 exceed his revenue, so his net is effectively 0. Okay, so then you start bumping it up to $3, and you start thinking about the kind of net returns that farmer is going to make. And right, think about, most of you probably know what your parents make, right? And think about, right, if the costs, and I can tell you that the costs are about $2 a bushel to grow corn in the United States today, right? By the time you buy the seed and the fertilizer, et cetera, et cetera. So you start doing the math of what does it need to be to make an income on a 2,000 acre corn farm. It's not easy. They view, I assure you, if I was giving this talk in Des Moines, market good. Okay, intriguing. Okay, let's go back. Let's vote again. Just see, I think people still believe biofuels are going to cause food prices to rise, despite all that yield potential in the world. Okay, so it's lower down. So again, we're making some progress here. Let's hide and stop. But I don't have a slide to illustrate it, but the corn acreage of, and I keep talking about corn, a twitch or something, okay? But the corn acreage of Africa is approximately equivalent to the corn acreage of North America. It's about 85 million acres, right? The yields are 500% lower. So there's this vast yield potential in the world that we need to begin to take advantage of. Indirect land use conversion. Here's a fun one. The deep thought here is that if I take an acre, and again, people are going to use corn, but the argument would hold true for switchgrass. If I put an acre of cropland into fuel production in the United States, oh, somebody must cut down an acre of Brazilian rainforest as a response, right? So it assumes that agriculture is like a balloon. If I step on it here, right, it has to balloon out over there. Based on what I've told you, does anybody believe that's true? No, why? Because it's like office space in Manhattan, right? You can go up through yields. It doesn't seem to bear, the data doesn't seem to bear it out. So if we look, this is ethanol. This is corn used for fuel ethanol in the United States. This is our corn exports and our soybean exports. You should know that most farmers alternate corn and beans, okay, in the Midwest. This is a classic corn bean rotation. So if that was happening, if all of a sudden we had all this less corn and farmers were going to plant more corn, so you weren't going to have as much soybean, then wouldn't we be exporting less? But we're not exporting less. If anything, right, these stay the same. This one has actually gone up. So again, international land use changes, or Brazilian deforestation, driven by a lot of things, but lack of US grain exports is not one of them. Does anyone know what are the things that drive Brazilian deforestation? Poverty, number one, but cattle. What are some of Brazil's biggest exporters? Does anyone know? Cattle, chickens, soybeans, orange juice, right? Brazil is quickly becoming the breadbasket of the world. And so if you ask where is the Brazilian rainforest going, right? They're cutting it down, they're ranching, they're doing a lot of things with it. They're also growing incredibly low yielding corn and other crops. So they need to increase their agricultural productivity and stop cutting down forests. Sugarcane, it largely goes into the pampas. So they're not really replacing forest with sugarcane directly. So there's a few problems with these indirect land use models. One is, they sort of represent conventional wisdom, and the conventional wisdom on biofuels driving food prices has clearly been wrong. So I think you got to be wary of conventional wisdom the second time around. Science, as Bob will teach you, is a mechanism by which we generate hypotheses. We test those hypotheses against the available data, and if your hypothesis doesn't fit the data, what do? Daisy, what do? You discard that hypothesis, right? You were fast enough on the trigger there, right? You discard your hypothesis. You come up with another one. And so the problem with these indirect land use models that people have generated is that they don't backcast. Right? If I went back to 1940, and I know what's happened to global crop yield since 1940, and I try and apply these economic equilibrium models in 1940 and predict what the world would have looked like in 1960, they fail miserably. If I go back to 1965 and try and predict what the world looked like in 1980, they fail miserably. So you're trying to use them to forecast the future doesn't seem like I really want to bet the farm on it, okay? So there's all these other shortcomings, which I won't go into this week. Yeah, we're doing okay on time. Oh, look, let's vote again. People getting tired of this question yet? We get it. Come on. Oh, God, we still have some hot air UCLA professors. God bless you. Oh, they can't cause childhood obesity. Okay, sorry. I thought that was the hot air. It's, yeah, okay. All right, let's keep going here. So one of the things that we did is think a lot about the amount of land that you would need to do this at a material scale, okay? Because, 10 billion gallons is a lot, but we use something like, I'm trying to think, gasoline use in the United States. Anybody know what gasoline use is per day in the United States? Fun number. 100 million gallons a day, right? Or no, excuse me, 300 million gallons a day. 300 million gallons a day. It's about 100 million households in the United States. And on average, they use about 3 gallons of gasoline, right? Think about commuting to and from work, right? Driving your F-150, you commute a little bit further. But 300 million gallons a day, that's about what we use. So 10 billion gallons is a lot, but it's not enough. So not enough land. So about 2.3 billion acres in the United States. And you can bucket it out into almost 1 billion acres of forest. In fact, more forest in the United States today than at almost any other time since about the Civil War, believe it or not. About 480 million acres of farmland, about 600 million acres of rangeland, on which we're presumably grazing lots of cattle, and 460 million of golf courses and strip malls and homes, et cetera, et cetera. And you can break, and these are just arbitrary numbers to make the point, but you can break the farmland out to about 60 million acres of pasture. Take the bottom 10% yielding acres, call that 48 million of marginal acres. There's also about 40 million acres of idle land. If you've ever heard that the US government pays farmers not to farm, that's called the CRP program, and that's what that is. It's idle farmland that, quite frankly, the corn farmers came up with this idea to, surprise, drive corn prices up. Right? If we could take, if they figured, right, if they could take land out of production to get the government to pay for it, it would cause corn prices to rise. Didn't really work because yields continued to go up. Nonetheless, there's about, call it 5% of that rangeland that's also convertible into growing the kind of biomass crops that Cirrus develops. And then I took some portion of each of those, and I was surprised trying to get to 60 million acres, because when you run the math forward, again, not thinking about cornstarch, but thinking about biomass, if we take that 60 million acres and just run the math forward at 20 tons per acre and 100 gallons per ton, you get to about 85% of US gasoline demand. So you can get to E85, which is what Brazil is running on today. That's what you need to do it domestically, about 60 million acres. And it's there, it's available. Out of 2.3 billion acres, we can come up with 60 million. By the way, Monsanto and Pioneer's projections are that by 2030, average US corn yields will be at 300 bushels per acre versus the 158 or so today. And if you did that, you would meet your domestic corn requirements, right, which are largely going into animal feed, right? So not everybody has to go become a vegetarian. That you would do that on about 30 million acres. We planted about 90 million acres of corn last year, okay? So there's plenty of land. I did the same analysis globally. The UN breaks it out a little bit differently, so about 26 billion acres in the world. They break it out into forest land, cropland, pasture land, and then urbanization. And pasture land is incredibly, Chris Somerville gave me this, we still use, look at it, it's 26, we still use 25% of the Earth's surface to graze cattle. Not the most efficient thing to do, okay? But nonetheless, we do it. And so the math here was simply saying if we took 10% of the world's cropland, and I hope I've convinced you that crop yields can go up by a whole lot more than 10%, and 5% of the pasture land, completely arbitrary numbers, and then I ran it through the same 20 tons per acre, and here I converted to barrels. 88 million barrels per day is Well, I have to go back to last summer, but that's about what global oil production and consumption is, about 88 million barrels a day. So it can be a material source, right? If you look, as Steve Koonin would say, if you're looking for a material source of carbon-carbon bonds on the planet, the biomass resource, in fact, exceeds the fossil resource. And the fossil resource, where did that come from, guys? It all came from plant matter anyways. So those carbon-carbon bonds, right, when we take, do they know photosynthesis, right? When you take CO2 and you fix it together into those simple sugars, that's photosynthesis. Plants do that. And so that's what we're trying to do by making liquid transportation fuels from biomass, is close that carbon cycle. This is just kind of a fun idea. Anybody has any stock traders, any day traders? Come on. So oil companies, like many companies, they trade on the basis of their profits and losses, right? They also trade on the basis of what is called their proven reserves. So if you think about it, it's kind of a crazy long-term game to be in, right? They've got this big bucket of reserves into which they've stuck a big straw, into which they pump out oil and sell it. But they've got to replenish those reserves, because otherwise you're just going to slowly suck that out. So they spend a lot of money, a lot of money, going around looking for new reserves, okay? Well, let's assume, for the sake of argument here, that we have a cellulosic biorefinery. Here's one, right here. And all the biomass is local, right? You're not gonna put this in and then only have a contract for 1 year's worth of biomass. What's gonna happen the next year if the farmer decides to grow cotton or something, right? This plant is gonna sit idle. So chances are you're gonna put in place long-term contracts, and we're seeing this start to happen. So again, I'm just having fun with math here. So I assumed a 21-year contract, despite the plant life here is probably 50 years. 20 tons per acre, 100 gallons per ton, 42 gallons per barrel. You get about 1,000 barrels per acre off of that. Not bad. Now, how many refineries and how many acres might you have on a global basis? If you're ExxonMobil, you think you're gonna run one of these, right? No. So what I did was to imagine that on a global basis, that an ExxonMobil or a BP or whoever might have as much as 10 million acres under contract on a global basis. We're using 16 million acres of corn today for biofuels production. That's just the US. So 10 million acres globally doesn't seem to be that big of a stretch. But when you run that math forward, 10 million acres if you called it a renewable reserve, because the biomass grows back every year, that's 10 billion barrels. Right? This is the current proven reserves. This is actually a little old. These are 2004, right? Boy, if you're Chevron, you just doubled your proved reserves. So it's an interesting way to think about how biomass could be a renewable reserve and create economic incentives not only for refineries but for growers to do this. Sustainability is obviously important, and if you want to learn more about it, you can go to this NGO that I have to say that we helped set up, and I'm actually on the steering committee. It's called the Council for Sustainable Biomass Production. It's folks like ourselves. Chevron is involved. ConocoPhillips is there. BP is there. Unless you think it's the proverbial fox guarding the chicken coop. National Resources Defense Council, Environmental Defense, the Nature Conservancy, National Wildlife Federation are all part of this Sustainability Council on how we can come up with the kind of biomass and the scale of biomass resources that I've described and do that in a sustainable way. And it's all focused on biomass and second generation biofuels. This just looks at net energy and greenhouse gas production. This is a publication on switchgrass. I'll go through it pretty quickly, but this was some pretty low yielding switchgrass, so it got 540% more renewable than non-renewable, and the greenhouse gas reduction was 94%. So you can do this today. It's simply at what cost is the refining technology. So you're probably getting tired of hearing this, but I'm going to beat it into you anyways. Let's go through some thoughts on agriculture, because I'm not convinced that all of you believe that there's enough land and enough agricultural productivity in the world to do this. some perspective. We think the planet's about 4.6 billion years old. We think we've had unicellular life for about 3.5 billion years. We had the Cambrian explosion, it's probably up there, about 600 million years ago, which is multicellular organisms. We've had hominids, right, Lucy and whatnot, for about 7 million years. The last ice age ended about 18,000 years ago. We've only had agriculture for about 10,000 years. Modern humans have been around for about 250,000 years. And so the point is, agriculture is not natural. It's not. It's a distinctly human activity, okay? Should we even have it? Jared Diamond, is he still a professor here? Is he still in the faculty? Yeah. Jared called agriculture the worst mistake in the history of the human race, a catastrophe from which we've never recovered. Encyclopedia Britannica called it the single decisive factor that made it possible for us to settle in permanent civilizations. And if you compare the achievements of agrarian societies in art, music, literature, technology, medicine, and compare that to hunter-gatherer societies, there's no comparison. So we can go back to the Pleistocene, if that's what you want, right? If you want to keep everything in sort of this Pleistostatic, right? We'll go back, we'll recapitulate the prairies, we'll let everything grow back, but we're not going to have a lot of other things, so you're going to have to give up the iPods too. Plants did not evolve to serve man. Does anyone know what teosinte is? Anybody? Teosinte. Teosinte is corn.
Talked about it in the first day of class.
So teosinte is corn. Here, you know what teosinte is. You didn't speak up. So teosinte, here it is, right? This is corn. It is Zea mays, same species, okay? This is the fully fertile intermediate, okay? This is what we bred corn from. Okay? Humans did this, not nature. Okay? You think the genes have changed at all? You bet they have. Here's a wild tomato compared to a commercial cultivar. Carrots, and by the way, potatoes, are naturally purple. Right? You see the orange flesh on the inside. Anybody ever eat a purple carrot? Yeah, there you go. Okay? So we've been manipulating genes for the past 10,000 years to come up with these domesticated species that we use. Where can you get a purple carrot? Maybe the farmer's market. I don't see too many of them around. They're very bitter. Right, those purple compounds are anthocyanins that they taste bitter. So that's what's that purple lettuce that I hate? It's arugula. Right, the same sort of compounds, but there you have it. So what limits crop yields then? Well, the biggest limitation is probably genetics, right? As I just showed you, and you're probably familiar. None of you knew what teosinte was, but you're probably familiar with the genetic variation that occurs in corn, right? Indian corn, you've seen that, right? You're probably familiar with the genetic variation that occurs in a lot of other domesticated plants and animals, right? When you say dog, right, do you think of a Great Dane, or do you think of the thing that Paris Hilton keeps in her purse, right? They're both dogs, right? But they're hugely different in terms of their physical phenotype. Agriculture, right, is also subject to biotic stress, right? Insects, fungi, weeds get into your field, right? This purple, pretty purple flower is called stringa, and this is endemic in Africa. It's called strangleweed. Its roots actually grow down and grow around the corn roots and literally strangle off the nutrients of the corn. Number of companies developing herbicides against stringa, 0. Okay, hugely limiting in African agriculture. And then, of course, you're probably familiar with what we call abiotic stress: drought, nitrogen, temperature. I think it's also, obviously an advocate of agriculture, it's also important to realize that agriculture is not perfect, right? I don't think there's any other human activity that I can think of that replaces more biodiversity than agriculture, right? Hugely so, okay? So there's a loss of biodiversity, right? A cornfield is not a native prairie, okay? It has energy inputs. Nitrogen runoff is a problem that you've probably heard of, right? You have runoff into the Mississippi River, algae blooms in the Gulf of Mexico, so it's not perfect, right? But it can feed many, 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 many people. And if only the world's corn farmers achieved the US average yield, you could feed about 7.5 million people, just doing the math on just the corn acreage. Forget about the land that you used for rice or wheat or soybean or kumquats or anything else, okay? As vegetarians. So we go back to food as a public good. A lot of this is about food choices, right? We could make food really cheap if everybody just became a vegetarian, but are we going to force everybody to do that? And then, of course, if you went to the top 10% real, you guys can just read that, and that's just math. Another thing you might not realize is that technology is giving us more yield with less impact. And here's some data from the National Corn Growers Association. But if we look at nitrogen applied per bushel of corn produced, right, the trend line clearly down. Phosphate per bushel of corn produced, clearly down. No-till, very important. Conservation tillage is going up and continues to go up. And it largely gets enabled by ag biotech, which is another story for another time, I think. But that's clearly positive. I think there's a couple more in here. Herbicide use is going down. Insecticide use going down. So the adoption of technology all seems to be taking us in the right direction. So this course, what's the title of this course? It's about genetic engineering, somewhere in the title, isn't it? So these guys have had a little bit of exposure to that, yeah? So genetic engineering, what is biotechnology? Well, you guys have probably been exposed to sort of what I call basic one gene at a time recombinant DNA technology. Genomics is really the study of all the genes that are present in an organism, right, by using high throughput sequencing. Marker-assisted breeding is using DNA markers, so rather than just looking at the physical phenotypes of plants and deciding which crosses to make, we can look at the underlying genetic maps and decide that. And does anybody know who Craig Ventnor, have you talked about Craig Ventnor at all? Craig Ventnor is doing some very interesting work in synthetic biology, where he's literally tried to completely de novo synthesize a complete bacterial genome and is going to try and literally boot up a new form of life sometime in the next year, I think. He's going to be ready to do it. So synthetic biology, all of this is, of course, manipulating DNA and manipulating genes. Anybody knows what Moore's law is? Moore's law? Come on. Moore's law, Gordon Moore was a founder of Intel. And he came up with Moore's law. He said the number of transistors on a chip is going to double every 18 months, right? So the computing power of Bob's Mac here is probably exceeds all of what was in Houston's mission control in 1969 when they landed on the moon, right? So you're all familiar with the sort of the exponential increase we've had in computing power and the number of transistors on a chip. But the same thing is happening in the world of DNA, where the speed with which we can both sequence DNA and synthesize it is also increasing at an exponential rate. So technology improves, just as we saw earlier with agriculture, and it also accelerates, okay? And so we've moved well beyond sort of these single one gene at a time type technologies to the work that I described with people like Craig Ventnor, where we're actually synthesizing whole chromosomes. We have sort of standardized genes. Paul Ehrlich, anybody know who Paul Ehrlich is? Yeah, there you go. This is a book he wrote in 1968 called The Population Bomb. And these are some quotes from his book in 1968, basically saying that hundreds of millions of people were going to starve to death, right? India couldn't possibly feed itself by 1980, right? And what happened? Anyone know who Norman Borlaug is? Norman Borlaug was a wheat breeder. He won the Nobel Peace Prize in 1970 for ushering in what was called the Green Revolution, because he developed dwarf wheat varieties that effectively tripled global wheat production. And you can see these are yields in, I think, Mexico, India, and Pakistan. So innovation changes the game. Paul Ehrlich, who's still at Stanford, right, and he's a smart guy, but what did he do? He looked at population growth rates, and he looked at grain growth rates, and he just extrapolated out, right? Anybody, you guys must have run spreadsheets. If you just run your spreadsheet out of 1%, 1%, 1%, 1%, right? Those lines crossed. But he didn't think, right? This is the same problem with these indirect land use conversion models. They don't account for innovation, okay? Innovation occurs.